Hello, this is the first video in the Algorithm 2 series on efficiency and complexity for OCR Discrete further mathematics, and it introduces the ideas of efficiency and order of algorithms. This sort of measurement is very useful when an algorithm is to be run on a computer, as greater complexity may indicate a longer runtime or large amount of data storage space required. To compare how well algorithms work, we define the following. The size of a problem is a measure of how big it is. In the case of sorting algorithms, it is likely to be the number of elements in the list. For graphs and networks, it is likely to be the number of vertices, but could be specified as the number of arcs. We refer to the order of the algorithm to give an indication of its complexity. The terms complexity and order are often used interchangeably when describing the performance of an algorithm. The efficiency of an algorithm is a measure of the runtime of the algorithm, and in most cases is proportional to the number of operations that must be carried out. And the time complexity of an algorithm, denoted as T of n, is a measure of its efficiency or runtime as a function of the size of a problem. To work out how efficient an algorithm is, we can break it down into the number of steps that need to be done, generally assuming each step takes the same amount of time. Performing fewer steps to complete the same outcome makes an algorithm more efficient. We'll do an example of comparing and contrasting the efficiency and complexity of two algorithms in later videos. For a specific task, for example, sorting a given list of 10 numbers, we could directly compare two algorithms, count the steps taken, and decide which is more efficient. More usefully, we might want to compare the likely performance of our algorithms for some size of task n. In this case, we look at the worst case time complexity, which will be a function of n. If we consider what happens when n becomes very large, we can deduce the order of the algorithm. Let's look further at what we mean by the number of operations. Consider the number of operations required to evaluate the linear function f of x equals 2x plus 1. We'll use multiplication denoted by m and addition by a. So 2 times x plus 1 would be 1 multiplication and 1 addition. If we go on to consider the quadratic function f of x equals 3x squared plus 2x plus 1, you can see that that would be 3 times x plus 2 times x plus 1. If you look at the operations, that is 3 multiplications and 2 additions. However, if we rewrite f of x so that we have f of x equals 3x plus 2x plus 1, then we would have 3 times x plus 2 brackets times x plus 1, which reduces the number of multiplications to 2. We still have 2 additions. This way of rewriting the function of x is called a nested form. This nesting becomes increasingly useful as the order of the polynomial increases. So for a cubic function, f of x equals 4x cubed plus 3x squared plus 2x plus 1, for example, then you can see that when we write it out in the original form, we would have 6 multiplications and 3 additions. However, if we rewrite it in the nested form, that reduces down to 3 multiplications and 3 additions. Try this for yourself for a quartic polynomial function. You should get 10 multiplications and 4 additions compared with 4 multiplications and 4 additions. Or we can see that the nested method requires fewer operations. We can keep going and consider higher order polynomials to deduce what happens for a polynomial size n. But you are probably already getting the idea that if we summarize the results so far and generalized, we would see that method 1, we have the triangle numbers, whereas method 2 reduces the number of multiplications to just n for each time. hopefully you can remember the sum of the natural numbers or the triangle numbers from your core or pure work and other topics. If we look in more detail at that final row, we could now compare the time complexity of the methods. So, where K1 and K2 are constants associated with the amount of time required for a multiplication or an addition, then to find the order, we consider what happens as n becomes very large. Then the highest order of n will dominate. So, for example, the time complexity of K1 with n over n2 n plus 1 plus K2n will actually become a function mostly of n squared, and therefore we would say the order is n squared for method 1. For method 2, you can see that the time complexity function was based merely on K1n plus K2n, where K1 and K2 are constants, and therefore for method 2 it is simply of order n. Clearly then, the complexity as n grows, in other words, the number of items in a list or the number of vertices in a network, method 2 will be far less complex than method 1. Let us look at this simple example. Many processes have several stages, and finding the time complexity as an exact function may be difficult, but in this case we can estimate it. So if we had an algorithm, straightforward, simple 2 instructions, for organising a pile of n items of clothing for sale. So sort the clothing into piles of the same type, and then take each pile and sort it into order size. We can see that we'd only have to look at each once to decide which pile to put it in. However, with the taking each pile and sorting it into size order, sorting algorithms are generally of quadratic complexity, and we'll look at this further later on. Therefore, it is likely that the time complexity function is a function of n plus a function of n squared. But as the pile of clothing gets bigger and bigger, that n squared term will dominate. And therefore, we would say that time complexity has quadratic order, or order of n squared. Many of the algorithms you come across in this syllabus will be of quadratic or cubic order. You'd see this written as O(n squared) or O(n cubed, where n is the side of the problem, so look out for that when you are reading the questions. It's helpful because if you know the runtime for a particular value of n, you can then estimate the runtime for larger problems without needing to know the exact details of the algorithm. So we'll look at algorithms of polynomial order up to quartic in this syllabus. Some algorithms are said to have exponential complexity, for example when they are functions of n factorial or 2 to the power n. However, these are generally not practical for large problems because of the rate at which the runtime increases, and we won't look at these further. In the next video, 2.2, we will look at the efficiency and order of sorting algorithms.